Um, okay, so I think if I'll just introduce myself. My name's Patrick Ollerton, based in Manchester, UK. I have my wife Samantha and 2 children. I've been with PTC 24 years and started out in the PLM world as a consultant, then as a trainer for customers as well as internal staff, helping to develop our consultants. And then I was a process manager responsible for process definitions and process best practices around product architecture. That's really where I started to get interested in product architecture design, modular design, and systems engineering. And 2015, I was offered the product manager's job on Integrity Modeler, as it was then, now Windshield Modeler. Contact details are there. You can get me on LinkedIn or with my email. Feel free to get in touch. Let me get rid of that. Okay, so we have a YouTube channel. Just want to quickly advertise this. If you're not aware, you can find us with a search, Systems and Software Engineering, PTC. Please go and subscribe, take a look at any movies that are there, and you can learn information, obviously, about Modeler. We don't have much about RVNS at this point, but over time we'll put some more content relating to RVNS up there as well. And if this recording is nice and clean, we'll be putting this up there as well. Okay, so the first topic is what is systems engineering? And this is part of a larger training set of content. The agenda for that is shown here. So there's a lot of different topics. If you're interested in learning more about these areas, get in touch with me and we can help you get access to this training material. We're going to look at what is systems engineering, and the agenda is we'll look at product development in general, really take a step back outside of the PTC world and look at what is it that companies like PTC are trying to help our customers do. Then some explanations of what systems engineering is, then some information on how do we get started applying and using systems engineering. Then a bit more detail on the specific practices that are used and commonly used within systems engineering. And then some discussion around the future, and then a summary of what we've covered. Okay, so first of all, taking a step back, really, everybody at our company, PTC, are engaged in trying to help our customers make market-leading products and make new and innovative products more cost-effective with better market penetration. So how do we do this, and how can we help our customers achieve these goals? Well, if we consider some of the people that are doing this in the world today that are well known. I've picked out a few examples that probably all of us know. Elon Musk. First of all, so he was trained in physics and economics, which is an interesting mix of education, covering a wide spectrum. And what we've seen from his career over the last however long years, he pioneers new technology. That's a common trait. He combines those new technologies. And really, he creates new products and new markets. And one of his reasons for operating is to tackle the major challenges facing society, which is a pretty bold thing really to do. And he comes forward with bold solutions. So let's take a look at what he did. 2008, the first Tesla Roadster. Bonus points if you recognize what that car actually is. He basically took a Lotus Elise and put an electric motor inside it, which was a great first step, but a lot of the reviews, certainly the ones in my country, were pretty negative about this product. Not about the acceleration, that was fantastic, but the problem was, first of all, you've got to recharge these things. It's going to need a whole pack of batteries. So how did Elon Musk solve this? Well, he advanced battery technology and then built huge factories around the world to enable him to scale the business. So he came up with a really good idea, but the next few steps were much more difficult than the initial idea. The next problem that was always complained about by the market was, how do we charge these things? How do we go a long distance? They have a limited range. Well, that's the Tesla supercharger network today, which is incredible, and it's replicated across large parts of the world. So he's overcome the next problem, and going forward, another problem that he will have to deal with is battery recycling and dealing with these things. So they currently offer free battery recycling, and I think from 2008 to where we are today, they've pioneered the electric vehicle and then really perfected the productization and scaling up of the business. So really impressive. Another example, Tim Berners-Lee, who often gets called the person that invented the internet incorrectly. But he was one of the main authors on the Hypertext Transfer Protocol 1.0 at CERN. And he came up with the concept of hyperlinking. That computer that you see there is the world's first web server, where he was serving up content to remote machines publicly. So interestingly, his perspective, several years after he pioneered this new technology, he said it was already invented. He just had to put them together. It was a step of generalizing, going to a higher level of abstraction and thinking about all of the individual systems that were there and how we could bring them all together into one system of systems. So pretty interesting perspective. Someone else that we all know, Steve Jobs, of course, and the industrial designer that he worked with on the design team, Johnny Ive. These guys basically perfected several telecommunications products one by one. They weren't first to market, unlike people like Elon Musk, but they perfected the user experience, and they always provided integrated design. So they didn't rely on anybody else to provide the software. They provided everything that you needed. And the graphic there is quite interesting. That was the launch of the iPhone 1, where he was looking at some of these other products that were market leaders today. And he was comparing them to what he was about to show and highlighting the problems. Basically, what he was doing was saying that all of these are now obsolete. And so it's been proved. None of those products are really around, apart from maybe Nokia. So the experience there of tapping on a tiny keyboard that maybe a lot of us have done in the past was good, but really it was nowhere near where it needed to be. So with revolutionary design and a focus on the user experience and the functions, they were able to completely disrupt the industry, consign several big companies to the dustbin, to the trash can. As we all remember how big Nokia were 15 years ago, and BlackBerry as well. They disrupted the entire music industry with a new type of model. Obviously, the move to digital and now streaming was really put in place by a lot of the infrastructure that Apple put there with first the iPod, then the iPhone, and then the iPad. Someone else who's maybe not as famous, but someone who I admire greatly because he makes games that I like, is Shigeru Miyamoto. And he has always had the vision of integrated design. He created Mario, Zelda, Donkey Kong, and the handheld device you see there I've got in my loft. That's one of the first games machines I ever had. But he pioneered motion sense gaming with his Wii, which we probably all know about when it came out 15 years ago, and all of a sudden video games became interactive and physical. A completely new product that is now the norm with obviously Xbox and other competitors. So he always invented new software and invented new hardware to work together. Somebody else in a similar kind of industry is Alex Kipman. And there we see him with PTC's CEO, Jim Heppelmann, launching the HoloLens 2 and one of our PTC's customers, Howdens. And again, he was a pioneer of new technology. He combined new hardware and new software to create a completely new product. Still the market leader, first to market with enterprise scale augmented reality headwear. He initially founded Xbox Connect, So he took the next step from Miyamoto with motion sense gaming and perfected that with a new set of games. And that then led him to understanding the power of sensing the real world and leading to the HoloLens development. So something that we can draw from all of these people is that they display systems thinking. Throughout their career, they've combined and integrated new technologies to create new products. And this gives them the magic skills to innovate continually. So what is systems engineering? Here's a definition from Wikipedia, which is nice and simple to understand. Systems engineering is an interdisciplinary field of engineering and engineering management. So that's a really important first statement. It's interdisciplinary. So it looks to combine different types of engineering. And it also looks to combine the management of those engineering disciplines. So it really does try to bring everything together in terms of the different efforts needed for overall product development. The goal is to design, integrate, and manage complex systems over their life cycle. System engineering relies on systems thinking principles, like we've just seen in some of those examples. The result is an engineered system, which is a combination of components working together to perform a useful function. So that's a really good definition, I think, and very easy to understand and surmises the goals. One of the standards bodies involved in systems engineering is INCOSE, the International Council of Systems Engineering, and this is their definition. It's a little bit more wordy. Systems engineering is a transdisciplinary and integrative approach to enable the successful realization, use, and retirement of engineered systems. It uses systems principles and concepts and scientific, technological, and management methods. So it says the same thing as the last slide, slightly flowery language. This graphic is quite good. I think it shows some of the key aspects of systems engineering, risk management right at the top. One of the goals of systems engineering is to de-risk product design, to take the risk out of the design projects that we're undertaking. And some of the ways we do that is by understanding requirements, understanding the human factors, the outputs of building software and hardware, but we apply project leadership. There's an integration effort that's required and verification and validation. So highlighting some of the key aspects of systems engineering there. Okay, so let's sort of step back and think, when did systems engineering really start to appear in our world? Well, there were some of the characteristics of systems in ancient civilizations. Complex buildings, irrigation systems, sewage systems. They were pretty simple though. When we moved into the Industrial Revolution, the machine age, we started to create machine systems. They were primarily mechanical. They led to rapid mass production. But they were complex assembly lines with processes that could be described and then controls so we could measure. So we start to get into some of the traits that are essential for systems nowadays. As we moved into the space age, and the graphic is Apollo 11, first mission to the moon, we started to see very complex systems of systems with millions of components in them. They were very multidisciplinary, mechanical, electrical, software, telecoms, all needing to work together coherently. They were safety critical. So people's lives or serious loss of endangerment to life was part of the design challenge. And there were high costs, very high costs, which means a high price of failure. So this is what we see in a lot of product development today. Some examples of systems that we all know. The weather systems. So we all see these kind of graphics more and more as hurricanes fall over the Caribbean. The human body has many systems, and we hear about these, of course. Water cycle, another one we know very well. But more interesting to us are engineered systems, and some that are widely used. A very simple one is a bicycle. Not many components, but it actually produces something quite magical, really, once it's put together correctly and used correctly. Electric shavers, power tools, rechargeable batteries, showers. And these are some customers of Windshield Modeler, shown in the graphics there. Engineered systems typically have very clearly defined functions. They generally have a power source, involve human users, and provide a way to control the system. So these are pretty key characteristics, and they relate to the kind of things that we're interested in as systems engineers. It's understanding how to manage those, how to realize those functions, how to manage the power, how to provide the functions to the users, and how to give them mechanisms to control the system. Complex systems are where there's a really big challenge and where systems engineering solutions give most value. So engines, and some engines are quite simple, of course, but aerospace engines like the ones you see in the graphic are very complex. Aircraft in general, automobiles are more and more complex nowadays, especially as they have more sensoring and autonomous capabilities. Production lines, factories, construction equipment, trains and train networks, space equipment, medical equipment. All of these areas now have very complex products that are multidisciplinary. They have software, electrical, mechanical components. They may be very expensive, and there may be a safety risk. Most likely there's a safety risk if there's any kind of failure. So in these situations, it really pays for the people manufacturing and designing these systems, these products, to do the very best job they can and make sure that they get their designs 100% correct. So let's look at an example. How do we understand a really simple system like a bicycle? So we ask a series of questions. Who's going to use the system, first of all? Well, here's a bicycle, and here's my user. In this case, it's a child's bike, and that's my son. So the first question is, we've established who the user of the system will be. Where will they use it? We've got the environment captured. He's going to use it on roads, fields, and also ramps at sometimes as well. So we now know what environment our system operates in. What do they want the system to do? Well, the functions that the user wants are transport and fun. Probably fun first for a child's bike. So then the next question we ask is, what capabilities does the system need to provide? And this then gives us the behavior of the system. It needs to be able to move, steer, stop, and optionally jump. So this is the first phase of understanding what our users need, what functions need to be delivered, what environment the system will operate in. And the next phase is to think about how can we make that real? So what components are needed to realize that system that we've started to understand, and how are those components organized? So we then design a structure or a product architecture. In this case, we've gone with 2 wheels, standard diamond frame, suspension on the front forks, and 5 gears. So each of those is a conscious design decision that the engineers must make to deliver those functions and behavior. Next question is, what major subsystems are needed? So this is not very complex, but even with a simple bike, we can start to think, actually, there are subsystems here. There's a power subsystem, and it involves the legs from the user, the crank, the chain, the gears, and the wheels, All of those transmit the power to the bike, to the road. And that satisfies the behavior requirement that we have. So that enables the user to move the bike. The other system we have is the controls subsystem. The handlebars, that allows us to provide the steer behavior. We have brakes that will satisfy the stop behavior. And we have gear shifting as well to help us with move. So we can start to understand and allocate the components and the architecture to the behavior that we need to provide. And finally, how will it all work together? This is a key part of systems engineering, is to understand the interfaces within the system. So the first obvious one is that the user needs to use the pedals to turn the crank, to turn the chain, to turn the wheel. So those pedals must satisfy and must be able to take some pressure from a child's foot. We have handlebars. So the user puts his hands on the handlebars. We have another human interface here. The brakes, they obviously will stop the wheel. So there's a key interface between the brake itself and the rim of the wheel. The gears, several interfaces there. The pedals to the chain, to the gear system, the derailleur. The headset connects the handlebars to the forks. The wheels interface with the road. Usually in a system of components, you'll have many more interfaces than actual components because so many things are interacting. And understanding these is key to understanding where possible failures will occur. Okay, so why do we need this? Well, in today's market, we have raised consumer expectations. Customers expect personalization, optimum usability, total quality, no failures or product recalls, and security and safety. These are all given expectations now. They're not seen as high-performing product expectations. It's just for any product now. We've seen rapid technology advancements, and in our industry, we hear about a lot of these very regularly. Of course, the internet, web, cloud delivery, 3D printing, additive manufacturing, Internet of Things, mixed reality, artificial intelligence. All of these things are making technology move even faster. And there's a graphic from the author, credited at the bottom. And this shows how long it takes a lot of common products to penetrate the market. From the phone and the car 100 or so years ago, 150 years ago now really, taking many, many decades really to penetrate the market to a large percentage. In the modern day, we've seen that the PC has really become commonplace very quickly, and mobile phone even faster. So in some areas of industry, the acceptance and the advancement of products is very rapid. And we're seeing increased complexity of software, of systems, and of industry standards and regulations. So all of these things drive systems engineering. And really they are one side of the coin. The other side is, what are the goals of systems engineering? Really to satisfy those challenges. First of all, understand the needs and wants of the product consumers and stakeholders. So that's pretty obvious. Understand what the users need, but also the stakeholders that are involved. They may not be a direct user. Reduce overall product development time and costs. And the overall is in italics there because systems engineering is not a shortcut. It is not a way to do things in a more easy way. It's to do things with more rigor and more thoroughness. So you won't necessarily save time and costs in the short run, but in the long run you will, because you save on product failure, you improve product quality, you improve the product position in the marketplace through those things. So it requires some investment and commitment, but then you get the benefits throughout the rest of the product cycle. Increasing product quality, understanding what the product must do, and then delivering the capabilities so that they deliver those functions and that behavior without failure. And really what we want is to eliminate product failures altogether, also known as rapid unscheduled disassembly from Elon Musk. And I think he coined that when he was testing the SpaceX landing craft. There's a very good YouTube video that shows a lot of the landing testing that was done over the last 10 years or so for SpaceX, and obviously a lot of them crashed. So there was the movie gives a good analysis of what went wrong in each of the crashes that you see in a chronological time-based sequence. So it's quite funny, really, but this is the nature of developing new products, that failures occur. Some other goals that are maybe not as important, but still important: enabling design reuse. This helps to really reduce costs, reduce time, and make you, the people, the manufacturers and engineering companies, much more efficient. Enable variability. And this is similar to reusing your designs in a modular way. And also to foster innovation. Systems engineering must be seen as a structured, scientific way to help solve the problems of the world today. And that means innovating solutions to these problems. Okay, so how do we start to adopt and utilize systems engineering? There are some core principles and concepts that are pretty well established, and they're not new really, and they're not anything too clever. They're pretty obvious when understood. So first of all, we have to understand the requirements, both functional and non-functional. That's the first step. Understand what we need to do. Understand what the right functions are that are needed to satisfy those requirements. So they're very similar, but it's a slightly different perspective. And of course, this is all about listening to the users, understanding the domain, the environment that you're working in, understanding the stakeholders that are at play, and listening to what they need. A key aspect of systems engineering is a focus on the whole of the product, not just the individual components. So by nature, systems engineering must be holistic. It must look at the big picture all the time. You go into detail, but then step back to see the big result. And it must be interdisciplinary to do that. Systems should provide more than the sum of their parts. And this is the notion of emergent properties. When you combine bits of a solution together, you actually get more. And this is pretty common with lots of examples of systems. Something else that we must think about in systems engineering is to understand dynamic interaction and change over time, not just an examination or understanding of static structures. And we'll look at that in more detail and explain what that means in the coming slides. Some of the principles: managing complexity with decomposition. So a complex problem needs to be broken up into bits. And ideally, we think as well about modularity. And the graphic shows Lego. They're probably one of the best examples of a simple example of modularity. And that particular product, you can create 3 distinct vehicles from the same set of bricks. But of course, we all know Lego, and you can create 1 million different things from the same set of bricks. In terms of in real life, when we're working with more complex products, the goal here is to define and optimize the overall architecture. So we need to define subsystems, modules where possible, and then the lower level components. and then how they interact and what those interfaces are. So that's one of the first steps, is to really think about the architecture and how you decompose the solution. Reuse designs where possible. So this is a benefit and combines with modularity. So the graphic shows Volkswagen's MQB platform that you probably are aware of, and this enables Volkswagen to create many different types of product offerings from the same base engineering solution. And it was configurable, so you could actually change the dimensions for smaller or longer wheelbases, and it would readjust its overall design architecture to support that. So the transmission, the axles, and everything else was repositioned based on that wheelbase. And all of the CAD models that were needed to support all of this, the manufacturing plans needed to support all of this, were configurable as well. So it was a very, very efficient platform, and still is, for creating lots of different product offerings from really the same solution underneath. So platform awareness and reuse of design, very important. And then verifying system designs. So the quote from Elon Musk is quite good. Failure is an option. If things are not failing, you're not innovating enough. And I think that's probably, I'm not sure he meant it quite as it reads, but I think we all understand what he means here, that if you're just doing the simple things, you'll come out with a simple solution. And we need to be really solving the complex, challenging problems. So really that means verifying the system designs is a critical step in systems engineering. It proves that all of the work you've done before has been the right thing to do. It proves that the designs you have constructed and created will solve the problem that we're trying to solve. So we need to do reviews of the models, reviews of the designs, engineering analysis, and simulation where we can. And this should focus on understanding possible risks, possible failure conditions, and the underlying causes. And then, of course, with a feedback loop into the design so that we can overcome, mitigate, eliminate any of these failure conditions and causes. Okay, so aside from those concepts, some others that are pretty well established in industry, the notion of RFLP. This is a simplified way of looking at systems engineering, showing the main phases and deliverables. And really, it's there to try and ensure all requirements and use cases are satisfied, all functions are provided, and then there's clear traceability. So we start with requirements, then we define functions, and the functions need to realize those requirements. Otherwise, why are we providing them? Then we can define the logical structure, which is the system blocks, the system structure hierarchy. And these should satisfy or be allocated to use cases. And then we have the physical structure. And we say in general terms that the physical components implement the logical structure. And we can see end-to-end traceability, and then ensure that we have coverage, that all requirements are met, all functions are delivered. So that's just a simple way of looking at it. As I mentioned earlier, one of the key things is to define product architectures. So this is how the components or elements of a product are organized. And really, it's about how do we allocate the functions of the product to the logical and physical components? What is going to be actually realized in the physical sense to enable the delivery of those functions? And all products have an architecture. So we need to keep this in mind as we start to design the solution. Systems engineering strives to optimize architecture complexity. We're delivering complex systems, so we need to optimize that so it's not any more complex than it needs to be. The end users will interact with the system, and we need to design it in such a way that it's not too complex for them to use. So there's an internal and an external view there. And the graphic shows two levels of abstraction. So systems engineering tools like Modeler capture and define the logical architecture. The physical architecture would be in PLM systems like Windchill PLM. There are two main types of architecture, two main approaches, integral and modular. So let's see some examples of those. This is an example of an integral architecture, and this has come from a really old article or piece of research from Ulrich. You see reference at the bottom there, 95. So these principles are not new. In this case, we have complex coupling between the functions and the assemblies. So the assemblies work together to deliver the functions. They're spread across different chunks of the solution. It generally gives the best performance because it's designed to do the job perfectly. The boundaries might be difficult to establish though, and that means when you modify parts of the system, it will have an impact on the rest of the product. And it might be difficult to understand what impact that is. So although this might give the best performance, it's very difficult to maintain and it's not very efficient. Modular architecture has a more clear coupling between functions and modules. There's well-defined interactions between the modules. There's high flexibility with product variants. So it's easier to sort of remove a module or add a module because the interactions are more clear. We can modify one of the chunks or one of the modules, and it shouldn't have a major impact on other parts of the system. If it does, we can see and understand that quite clearly. So generally, a modular architecture is preferable. It's more efficient. It's a better structure, better organized. It helps with maintenance and change and reuse. But generally, products are not 100% modular or integral. There are always a combination of both. But this is a good goal, to have platforms at the top level of a system defined in a modular way. That way you can maintain them, you can engineer and manufacture them efficiently, and when you make changes, things don't get broken easily. If we look at that in how it plays out in a simple example, if we have integrated designs, we have 4 separate designs, which gives us 4 product offerings. If we add a new design, we end up with 5 variants or product offerings. If we have a platform with 3 optional modules, that gives us 8 variants. If we add 1 new variant, 1 new module, we get 8 more product offerings. So we get more of an exponential growth in the number of variants that we can offer when we use a platform and a modular design. And obviously, when we look at companies like Volkswagen, I think the number of variants that they have across their product range is a very large number. So managing all of this is incredibly difficult for our customers. Modularity enables combinations of variants, which creates greater variety in the product portfolio at a lower cost. We don't want to have to manage individual designs for all of these variants. Really, we need to be reusing a modular platform. Okay, so what are common practices? So we've probably heard and seen most of these, but I will go through them. First of all, the engineering V model. So this is well used and well known within systems engineering. It shows the main activities, the main phases, and the main deliverables. So we do some requirements analysis, architecture design, detailed design, integration and testing at the sort of subsystem unit level, verification and validation across all of these phases. It's widely used and adopted. It's simple and easy to understand. And as we know, PTC provides software that covers all of these phases. Requirements through RVNS, Windshield Modeler for architecture design and systems modeling, Windshield PLM for detailed design with Creo, Windshield Modeler for simulation and Creo Ansys and Creo Sim, and then Windshield RVNS for validation. MBSE is a well-established approach, really a methodology, and its definition from INCOSE is the formalized application of modeling. So that's key, that we're actually going to do some proper modeling to support system requirements, design, analysis, verification and validation activities, really throughout the life cycle, from conceptual design through development, testing and operation. So I think that's a pretty good definition, and MBSE looks to build on everything that we've seen so far and use a lot of these principles and concepts and provide a structured, systematic solution to actually realizing systems engineering. So it's a proven methodology. It can scale and handle complexity. So when we want to actually design very complex systems, MBSE is a good approach. Document or file-based approaches, maybe using Excel to define your architecture or a structured database, they become very challenging once you get to very complex solutions and systems. It's graphical, so it's easy to understand complex solutions, much more than just text or numbers. And I'm sure we all agree with that. That certainly makes sense. Understanding a complex product with millions of components in a spreadsheet is not really advisable. The visual nature helps understand the design dependencies. So it's very easy to create different structures of information and then connect them all together. So you understand the dependencies from the requirements to the functions, to the logical structure, to the system analysis that you can do. And again, very difficult with other approaches. So typically SysML is the language notation that's used for MBSE. So let's have a quick look at that. SysML provides a graphical notation and a semantic definition for what each of these things are. Requirements to use cases, then to scenarios or sequences that show the process steps. Activities which show an internal process, states which show the sort of operating states, the operating conditions of the system. This area in the bottom left shows in a lot of cases quite similar information, but it has a slightly different perspective and a slightly different purpose. Together, they work together to give you a complete picture of the system. And they're all about analyzing the behavior of the system. Are we delivering those functions? What are the steps the user will go through? What sort of buttons and process will they press to trigger those functions? How does it interact with the system in the activities? And then what are the operating conditions, and how do we trigger and transition from one state to another state? So this shows the rigorous nature of SysML and MBSE. The next side of the slide looks more really at the realization of the system. How do we make that real? So first of all, from the high level, we understand the environment and what system architecture we need. So that's really the system architecture. The block structure shows the internal connections. So the links that you can see between the blocks shows ports and connectors between those ports. So wherever there's an interface, wherever there's any interaction between parts of our system, we can capture and track and specify how they behave. One simple example would be kind of managing and modeling fuel flow. If we had a fuel pump into an engine, we'd want to understand how we manage that fuel flow. There'd need to be some controls on the system to make the fuel flow into the system. Maybe if it's a car, we're depressing the throttle pedal. And we need to understand how the system actually does that. So what are the components that are involved in making the fuel pump from the fuel reservoir into the engine? And how do we control it? We can go the next level and actually specify the engineering equations that are at play here. So whatever type of engineering the system is working in, we can define the equations and the engineering mathematics that describe that behavior in concrete terms. So when we do this, the model actually becomes something that's executable. It's something that we can kind of turn on and perform the functions. We'd put a wrapper around it so that we can kind of trigger things, but it gives you the ability to, as I say, execute the model and simulate it as if it's actually running. Understand the behavior, understand the functions, and check they deliver what's needed. So that's SysML. One of the other approaches is UML. Now this is for software engineering, model-based software engineering, not for model-based systems engineering, but it's closely related to SysML because a lot of our systems are software and hardware and physical components. So often we're combining UML designs with SysML. There's another framework provided by OMG, and it's very commonly used in aerospace, defense, and military. And it's a bit broader. It's an overall architecture framework. So it can be used for providing and modeling missions, campaigns, long-term enterprises, as well as products. As I mentioned a moment ago, review, analysis, and simulation is a really key part of MBSE. And we can visually simulate system model functionality. We can record the results for analysis, and we can perform design and model reviews. So some of the graphics there show we've got a systems model, and then we've simulated it and we've put a mock-up user interface on top so that we can see exactly what's going on. And then we can execute the behavior of the system and check that it performs as we need it to. The graphic on the top right is actually a mining system where we're tracking and simulating the movement of trucks in a mining environment. So it can have very broad capabilities in terms of what you analyze. And then we have another tool called Reviewer, which is really aimed more at checking the model and the designs are correct, complete, and compliant. So really in this area, we're trying to answer the questions. Does the system satisfy the requirements? Does the system deliver the required functions? Is the design complete? Is it correct according to our standards? Is it compliant with whatever policies and regulations that we may have in place? So again, if we go back to the original goals of systems engineering, it's to help de-risk the design. So we eliminate the chance of product failure, and conducting thorough simulation, thorough analysis and review is a really big part of that. Something else we can do, and it's quite common in systems engineering, is doing trade-off studies or trade studies. And that's really trying to find the optimum product solution. So maybe we'd compare different types of architecture, different features, different behavior, different performance. And we can run simulations, get some results back, and then compare and contrast the behavior and the output. It allows us to sort of explore the design space and come up with different ideas on how best to deliver the capabilities needed. It gives you some concrete information that allows you to assess your different design alternatives. And this is a tool that we connect to, or Windchill Modeler can integrate with, called Ansys Model Center, that enables you to run these sort of what-if design simulations. Another method that's quite common is design structure matrices, originally devised by Stephen Eppinger at MIT. And in terms of product architecture, they're used to understand the elements of a product, what interactions and interfaces occur. And then if we look at the grid here, we compare element A with element B, element A with element B, and then C, and then D, and then E, and then F, and then G. And wherever there's an interaction, we mark in that cell. So we can see that element A has an interface with B and F. And it helps to expose problems or opportunities within the organization, the architecture of that product. Maybe things need to be more closely coupled together or grouped together, or maybe things should be decoupled so they can become more modular. It's quite difficult to understand until you start using it, but it's a powerful tool to analyze an architecture. It's also called an n-squared chart. And here's an example from the original research from MIT for Pratt & Whitney aerospace engine. And you can see some of the patterns that you see in a more complex DSM help you identify modules where things interact closely, and then help you understand where there is distribution across the system. So maybe things need to be more closely connected, or at least physically near to each other to work correctly. Something else that's more and more common is OPM, object process methodology. It's kind of similar to SysML, but it's a little bit more generic and simple, I would say. It's a useful methodology. It focuses on objects and processes, and then the states of those objects. The processes transform objects, changing its state. So there are diagrams, and there's a notation, a graphical notation, as you can see here. I've never really used this. I don't have a great deal of experience with it, but certainly some of our customers have mentioned OPM, and it is taught in quite a few big universities. So I think what we've provided in the past here is a profile in Modeler, which is a customization, an extension that supports OPM. So Modeler can be quite easily tailored to this kind of methodology. Okay, what's the future? Well, we have SysML 2.0, the next generation of SysML, on the horizon. This will be released sometime this year, towards the back end of this year. And the goals are really to increase adoption and effectiveness of MBSE. PTC have been involved in the initial request and the development of the specification and the solution. We'll be delivering the first phase of our SysML 2.0 solution in Windchill Modeler 10.0. So this is quite a big milestone for the industry, a whole new standard that will improve on V1 of SysML 2. It will give more power, more expressiveness, so we can capture systems more accurately and effectively. It provides standard APIs, so it should be easier to share information as well, and you'll see that OSLC is part of that. REST and OSLC web services to expose SysML2 data. And there's a textual notation up at the top there that you can see, which is essentially some code that you can use to generate and define the model. And really the graphical view and the textual view, it's the same model. It's just a different representation of the model, which of course in Windchill Modeler is stored in a database in tables. So it's going to be an interesting period for our industry and an opportunity for us to really provide an excellent SysML 2.0 solution. If we look at what Incosi is saying, they host quite a few conferences and they publish information about the future. And what they've been saying recently are, we need to do a better job in considering humans as part of the system. We need to bridge the gap that still exists between software and physical systems. There's still a disconnect. We need to handle the exponential increase in scale and complexity. Utilize quantum engineering. I won't pretend to be an expert on that topic, so that's obviously an emerging science. Quantum computing is making progress, and engineering will be looking to take advantage of those principles. Incorporate artificial intelligence and safely. I think we'd all recognize that's a huge challenge going ahead, that artificial intelligence offers great potential, but we need to make sure that it doesn't have unintended consequences. And certainly sustainability and conservation of resources will be a huge challenge for systems engineering to solve going forward. Okay, so summary. Systems engineering is vital in the development of complex, safety-critical products. Provides a scientific, systematic approach to product development that improves quality, reduces cost, and drives innovation. And we see it time and time again. MBSE is the most robust, scalable, proven, and widely adopted methodology for systems engineering. Often, though, systems engineers are not really called that. They might be called product managers, head engineers or lead engineers, chief architect, or sometimes just inventors. Okay, thank you for your time, everybody.